All right, we're live. I'll just wait 1 minute for any possible latecomers. All right. Hello, everyone. I would like to welcome all of you to the Kubernetes Explained Netcompany Global Tech Talk. Um, Let me just switch to my presentation. Right, let's look into the agenda for tonight. I split my presentation into 5 parts. I would like to start with a short introduction, just to give you a grasp of how Kubernetes fits into the technology landscape, especially in the historical context. I will follow up on with an overview of the basic building blocks of technology, and that will conclude the basic part. Afterwards, I would like to present a deep dive into very granular details of the atomic units of scheduling. Right, known as pods. I'll go over architectural decisions and design patterns related to the pods. I'll show how one can leverage the deployment resource to implement features such as zero downtime updates. I'll also discuss the topic of imperative versus declarative way of handling Kubernetes. Next, I'm going to go over some security issues and conclude my talk by zooming in on the innards of the Kubernetes system. A few words about me. My name is Krzysztof. I work at Netcompany as a senior consultant. My main area of professional focus are DevOps and Java development. I've been participating in several processes of setting up greenfield projects that run on Kubernetes and migrating existing solutions to the containerized world. I currently play the role of technical leader on one of the teams in the Digital Pros project conducted for the Danish government. I maybe have a few words on that later. I'm just looking at the comments in the meantime. Uh, I've seen that the microphone was a bit low. I hope it's better right now. Also, there's one more thought I would like to share with you before we begin. Namely, preparing tech talks that serve as an overview for a technology is always a bit of a challenge. This is because the audience most likely consists of both people who are already familiar with the technology and people who aren't necessarily familiar but are eager to learn about it. I'll try to strike a reasonably good balance between explaining the entry-level stuff and the complex concepts. Just keep in mind that Kubernetes is a convoluted piece of technology, so if you miss something, feel free to ask during our Q&A session at the end of the talk. I do have an overview over the chat, as I said, and if there are some technical issues, please let me know. Also, bear in mind that there's some delay on the stream, so I won't be seeing comments immediately. And now, without any further ado, let's jump into the topic. The question I would like to answer first is, why would I need Kubernetes? Some people just land in a project with this technology or decide to use it because of all the hype around it. But why would an architect designing the infrastructure choose it? Let us go on a short journey back in time to the times when containerization and virtualization wasn't a thing. So applications run on servers. And in the past, we could only run one application per server. We didn't have the technology to safely run multiple applications on the same server, and it was a difficult fit altogether. So whenever business needed a new application, they had to buy a new machine. The problem was at that point they had no idea about the performance requirements of the application, etc. The costs of such a machine were huge, and no one would risk buying too little resources. If the server wasn't strong enough, it would lead to performance issues, lost customers, lost revenue, and eventually it would lead to IT department buying a new machine, effectively wasting a lot of money. So imagine a chain of pragmatic decisions, overestimations, and buffers resulting in buying a humongous server, which was the definite overkill for the application that it was supposed to serve. According to Nigel Poulton, who's a great author writing on Docker, the consequence of such decisions were a huge amount of servers operating as low as 5 to 10% of their potential capacity. A tragic waste of company capital and resources, says Nigel. Then, at the turn of the century, a company, VMware, emerged. They gave the world a wonderful gift, the VMware Workstation, a virtual machine. It's good to know that the virtual machines were available before. IBM worked on the concept as early as 1960s. Nevertheless, it was VMware that sparked the boom of virtual machines in the early 2000s. So, what's the deal with the virtual machine? Virtual machines allowed to run more than one operating system on one machine. It meant that you could safely and securely run multiple business applications on a single server. It not only allowed you to start using this 90% of spare capacity you had gathering dust in your company's basement, uh, you didn't have to buy a new oversized server every time the business needed a new application. From my perspective, the coolest thing the virtualization achieved was separating application from infrastructure. The one-to-one assignment that was that was before was changed to one-to-many, and the servers started to migrate from a mainframe with a name tag and a dedicated application that runs on it into a more abstract entity called resource. This entity could then be segmented freely to host different applications. In my opinion, virtualization was the first time we observed the notion of treating our infrastructure more like a cattle than like pets. It means that we don't hold sentiment to our resources. They're just that, resources. And starting from virtualization, this notion grows stronger and stronger, achieving milestones such as the idea of infrastructure as a code. The problem with virtualization lies in its very concept. Uh, we split a physical machine into separate virtual ones, each of them running completely separately. In this scenario, every VM requires its own dedicated operating system. The operating system consumes RAM, consumes CPU, consumes storage that could otherwise be used to power the applications. Additionally, operating systems require frequent patching. Some of them require license. It greatly increases the costs of maintaining them. Other disadvantages of VMs are slow booting. You're booting the entire operating system. It does take some time. Migrating workloads between VMs is difficult. Also, the separation between the VM and the application that runs on it meant that the VM had to be very precisely set up to facilitate the application. Uh, Also, if you look at the visual representation of our machine, we still end up losing, maybe wasting some resources. So I left space here to visualize it. And in such a scenario, you cannot create a new machine as you barely have enough resources to run an operating system. Somewhere around 2010s, early 2010s, a new paradigm was beginning to attract more and more attention. It was called containerization. Similarly to the story of VMware, Linux containers were developed earlier, but it was 7 years ago when Docker presented its tool for containers. That was when this new paradigm really took off. So the most important thing that Docker did was making containers simple. It made them accessible to all developers, not only to researchers in the tech giants. Containerization solved the essential problem of virtualization, which is resources being wasted on operating a system. Can you run 100 containers on your laptop? Well, I tried, and yes, you can. Imagine running 100 virtual machines on the same machine. Hardly doable, is it? Containers are quick to start, typically lightweight, and containing only the important modules. They're also mortal. The moment the main process of the container stops running, the container dies. One more note, I compared containers to virtual machines, but it isn't the most fortunate comparison. I tried to accentuate it a bit better with the color coding. Containers having the same color as the application on the previous slide. Containers are not the means of virtualization, but rather a means of delivering software. They're artifact. So the container is an artifact encapsulating binaries of an application, its file system, its runtime environment, etc. So again, they're not the infrastructure layer. The Docker daemon is the infrastructure layer, and containers are the application layer. There are also more tools that allow you to run containers than just Docker, but right now it's not relevant and we'll just stick with Docker. People quickly realized that containers provide a lot of flexibility, but they are not by themselves enough to run production-grade systems. Running a single application container locally is simple, but how to manage thousands of them? In order to run production-grade systems, we need to provide routing, balancing, um, security control planes, persistence, zero downtime updates, rollbacks, failover strategies, a lot of things. How to implement all of it with only simple Docker interface? After all, it only allows you to run single containers and operates on them as the basic units. Enter container orchestration. The container orchestrators build an abstraction layer on top of the containers. Generally speaking, they are responsible for managing the container's lifecycle. They serve as the infrastructure on which our application containers are run and add essential tooling such as networking, storage, and relevant control planes. Several orchestrators appeared just after Docker revolutionized the IT world with the popularization of containers. The three most thriving ones were Apache Mesos, Docker Swarm, and Google's Kubernetes. I'd say around 2 years ago, it was quite clear that the latter was the winner. So Kubernetes was the winner. And even Docker switched to Kubernetes as the default orchestrator, even though they have their proprietary Docker Swarm. One more note, there's also Red Hat's OpenShift, which is a fork of the upstream Kubernetes with some extended functionalities, such a nice graphical user interface, a built-in Docker registry, and some convenient tooling. Google now says that the biggest advantage they had over their competitors was open sourcing the project and democratizing the way Kubernetes is developed by donating it to CNCF, that's Cloud Native Computing Foundation. They set up open governance and generally establish transparency of how the product is enriched with new features. It's quite an interesting story, and donating to CNCF caused the emergence of an entire ecosystem of applications. These were only applications, these were mostly tooling, plugins, etc., that complement Kubernetes and build around it. I'll discuss some of them afterwards. Excuse me. Now, because containers are essentially, they contain the runtime environment and run on the standardized Docker engine, we actually introduce an abstraction layer on top of the previously used virtual machines here. We won't think about the machines as separate entities. Let us look at a simple example of how it's done in Kubernetes. This is a 30,000 foot view of Kubernetes. In general, it consists of a couple of VMs with an API layer on top. These don't have to be virtual machines. You can also run them on physical machines, but let's just go with the virtual ones for now. What Kubernetes does is it creates a uniform cluster out of these machines. In order to do so, it needs to install some specific software and do some configuration on the machines. Now, there are two ways these machines can be labeled. At least one of them will be labeled as master. The machine will be the brains. It'll be responsible for exposing the kube API, which is used to communicate with the cluster from the client. It'll usually have more responsibilities, but more on that later. There should be at least one master. When running on production, you need more than one for redundancy. The second label is a worker or simply a node. These machines are only responsible for running workloads. It's worth noting that while you can also run workloads on master, the workers are the ones doing the legwork. The process of assigning a workload to a node is called scheduling, and it is done by master. In my opinion, the crucial advantage here is the modularity. Notice how, from the perspective of a client communicating with the API, we do not know and do not care how many worker machines are there and what type of machines are those. We don't even know anything about the machine hosting the API server. This way, we don't get too attached to our infrastructure and are kind of forced to think about the cluster as a cluster of resources, not a known number of known machines. This brings us to the next question. How can we host our Kubernetes cluster? A good way to start is a managed service on one of the public clouds. We have AKS, that's Azure Kubernetes System. On Azure, we have EKS. On AWS, that's Elastic Kubernetes Service. Also, there is GKE on Google Cloud, that's Google Kubernetes Engine, if I'm not mistaken. These are the three biggest. Now, there are a lot of more clouds, but I just give those three as an example, and these are usually considered the three biggest, and yeah, giving us examples. You can also host a non-managed cluster on the cloud. Yeah, maybe I'll hide it. So yeah, a short story here. I happened to install an OpenShift cluster, which, as I mentioned, is a Red Hat's variation Kubernetes. I tried installing it on Azure, and the best thing they offered at the time was a GitHub repository with tens of ugly Ansible playbooks and even uglier PowerShell scripts that magically installed the cluster. Obviously, it didn't go as intended, but ultimately, after many tries, managed to get it installed. But when the time for updating the version came, we decided to forget about this cluster and simply migrate it to a managed service. And it was we consider it a very good choice. So the public cloud is one way to go. What are the other? Yeah, so you can go with a so-called private cloud. This approach basically means that you don't want to run your workloads and store your data in a computer owned by someone else, because that's what the cloud is. Instead, you prefer to keep your servers in your basement. It's a bit of a simplified explanation, but the main point is that you do not allow the data to leave your premise. There are obviously more reasons why you would run a private cloud instead of public cloud, uh, but these are just examples. Such an approach is usually taken by companies that operate on sensitive data, so for example, public sector. But yeah, not only. For local development, or if you don't want to pay, you can use Minikube distribution. It's very good for testing, for playing with some new ideas. Docker installs it for you together with Docker Desktop. Right now, it's a one VM setup, so you're essentially running everything on a master VM. Another cool thing is that Kubernetes can also be run in your browser, kind of. So there's a website called Katacoda, and it's probably the best place to play around and run some simple experiments. Um, Apart from that, you can apparently run Kubernetes on Raspberry Pi. It started as a cool experiment from several guys, but currently you can find a couple of full-blown tutorial series of how to create a cluster of several Raspberry Pis. Right. We went through the history and got ourselves a high-level overview. Let's look into the basic, say, building blocks, the basic units in Kubernetes. The first object is a pod. So a pod is an atomic unit of scheduling. It means that you cannot run anything smaller than the pod. A typical pod consists of one container plus some metadata and some configuration relevant for Kubernetes. In order to create the pod resource on Kubernetes, we need to post its definition to the API server. We do it using kubectl client. There are several ways of creating a pod. You can either post it using an imperative call, you can prepare a YAML template, but yeah, let's see how it's done. So this is my console. I have Kubernetes client installed. I also have Minikube running locally. The client, as I mentioned, is called kubectl. Some people pronounce it kubectl. I've heard that you should pronounce it kubecontrol. It doesn't really matter. The client comes with a rich documentation and it's overall quite easy to learn once you get the basics figured out. So let us run a pod. First, I'm going to run a command that will tell Kubernetes to run a pod. It will run a pod called nginx. Use nginx image to do so. We pass image flag here to specify it. And also there is the restart flag, but that's just technicality for now. Let us see how our pod is doing. It's fine, it's running. So far, so good. I said that we can describe the pod with a YAML file so that pods have YAML templates. Let's see how the file would look like. All right, so the only things, this is the YAML, let's say, template of a pod. The only thing right now that it has is saying that it's a pod. Yeah, it has some labels which are metadata. So, and yeah, it also has description of a container, the image, the name of the container. So let's create the pod using a YAML description. So I will put the description into a pod.yaml file. There it is. There's also a second file, but we'll get to that later. I can just to prove you that this is the same file. And now we can run kubectl apply to use the template, post it to Kubernetes, and get it started. Right now, yeah, maybe let's just give it several seconds. As you can see, I ran the get pods too early and we had container creating. Right now it's running. It took several seconds, so in 10 seconds it was ready. With some extra configuration, we could, for example, expose the Nginx service and access it, but for now, let's just clean up and get back to the presentation. All right. A more advanced pod may consist of several containers and volumes. The important thing is that a pod should functionally create a single application. Let's look at a simple canonical example. This example can be found in the book Kubernetes Up and Running, which I highly recommend. So suppose we have a container that serves web requests and using some file system. And there's another container synchronizing the file system with a remote Git repository. So this application, the one on here on top, is the one the user will be actually reaching. The other one is just a utility external to the application. The first step could be trying to put both Git sync application and web application in the same container somehow. However, after giving it some thought, it's clear that they have to be separated. First of all, the requirements are different, right? So the user-facing container is the important one. We need to make sure it's always available and responsive. The Git sync container, however, is not that important. Probably nobody will notice if it works a bit slower. Also, what if the Git sync container had a memory leak? Therefore, we would like to separate the main application and the supporting application into two separate containers, but still keep both of them in the same functional or logical module. One would think it makes no sense to have this application running on separate worker nodes because these are quite cohesive, right? We want to make sure that they are deployed on the same server. In such a use case, we would go with a multi-container pod. Before we get into more details of how pods are designed, what design patterns are there, we need to realize a fundamental flaw in the current approach. What happens if the container residing in a pod that we run dies? Well, nothing happens. We lose our application, it's no longer running. And this is obviously something that needs to be addressed. Also, what if you need multiple replicas of a pod? And there can be several reasons why you would need more than one copy of the application. So redundancy is one of them. It allows you to mitigate the failures of uh, single containers and make your system persistent through such events. Also, having multiple replicas allow you to scale to make sure you have enough resources to handle all the requests. You can also implement sharding, which means handling different parts of computation in parallel. So, in order to implement such replication, you wouldn't ask the user to define every pod separately. They're just copies. So Kubernetes introduces a concept called replica set. Replicas set adds two aspects to the pod. Firstly, the number of replicas, and secondly, the reconciliation loop. So running a pod is just telling Kubernetes to start several containers and forget about them, while running a replica set is telling Kubernetes to create a resource that will be responsible for controlling how many pods are running. In order to control the number of replicas, this resource has to be able to start new pods and kill pods that are over the limit. We have a first difference here between the imperative versus the declarative approach. So imperative means telling Kubernetes to do something and instructing it how to do it. It's giving a command. If you want to keep a pod running, however, you have to, so again, differently. If you want to keep a pod running, you have to create the pod and afterwards keep checking if it runs. If it dies, tough luck. You'll only know it when you check and you'll have to create a new one. The declarative style is very different. So you declare what you want and let Kubernetes do the thinking. Staying on the example of Replicas, you declare that you want such a pod running in so many copies and expect Kubernetes to deliver. In the example, we will have 3 replicas. And I'd like to emphasize that the declarative approach, so declarative nature of such an approach implicates the need of reconciliation loops, so constant checking and self-healing. And this loop will keep the requested number of pods and, for example, create a new one every time we lose one of the pods. One of the pods died, we got a new one. The general idea of declarative approach in the reconciliation loop is strongly connected to the notion of desired state versus the observed or current state. The observed state is what is happening on the cluster. One of the advantages of Kubernetes is its ability to perform continuous observation of the state present on the cluster and keep introducing changes to get the current state as close to the desired one as possible. Another thing, notice that Replicas builds a new new abstraction layer on top of pods. It's not yet the abstraction layer we wish for. We'll go 1, 2, even 3 steps further in order to run our applications, but it's very useful. The thing about Replicas is that it's very limited. In order to use Kubernetes efficiently, we need something that corresponds to an entire deployment of an application. We need something to manage, for example, releasing new versions of application to facilitate this. Something that can track the history of releases and can be used for rollbacks. Such an object is called deployment, and deployment is a resource built on top of Replica set. The main concern that deployment handles is rollout and rollback process. So we can define it like this, and we'll discuss in a moment. For now, let's jump into more advanced topics. Well, there's a lot to discuss in the rollout process that I will come back in the future. We need to look into the pods and go through several ideas connected with them. First of all, suppose you're working on a bigger scale project and you have multiple environments. There are a few low environments, typically called dev or test or whatnot. You can also have some environment for education purposes. On one of the projects I was working on, an education environment was used by the client to record videos for their employees and on how to use the software we're delivering. Quite an interesting case. Then you have a user acceptance test environment and some higher environments, let's say pre-production and production. Pre-production can be called staging. There are many different ways to call the environments. And again, it's just an example. So every project and every company will have their own variation of those. And let's take a moment to grasp the complexity of such a setup. If we're delivering a microservice with tens of applications and with a decent CI/CD flow, we're looking at tens or hundreds of deployments to different environments per day. That's easy to reach. Notice that the number of flow environments may also change rapidly. You might as well create them on demand and turn them down regularly. I want to so I want to emphasize that we'll be discussing an ecosystem of such complexity. So one thing we want to avoid at all costs is having to build our images with configuration for each of these environments because there are just so many. And there's a great practice of separating implementation from configuration, and we're aiming to introduce it here. So Docker images that we're delivering are artifacts, built once and promoted through environments, eventually reaching production if they're good enough. We want to make sure that the same image we deployed on the lowest environment is deployed to the production after we've proved it works as intended. Therefore, we cannot change the images that we deploy. They will be immutable. However, we also need to provide a different config. Therefore, we would like to externalize the configuration and supply it to our pods during deployment. Another concern is providing secrets. Passwords to databases, tokens, certificates, private keys. If we wanted to put them in Docker images keep them in plain text, it would very quickly be found by our operations or security team and regret it. Kubernetes offers a solution for these concerns. Solution number one, config map. Like any Kubernetes resource, it is described in the form of a YAML file. This resource contains a list of key value pairs that we can inject into the containers that we run in our pods. There are several ways we can do it. The first way is to have a list of environment variables and inject them to the environment of the application. A typical use case is injecting endpoints. These will very likely differ between environments. We can either inject several keys from our config map or just chuck the whole key value map into our runtime environment. Another slightly counterintuitive thing we can do with config map is putting a file into it. In such a scenario, we'll use the name of the file as the key and inline the content of the file as value. What you can do then is declare the config map as a volume and attach it to container. It's a bit tricky, but that's how configuration files are supplied in the Kubernetes world. A typical example I could give of such a scenario is providing logging config. You might want different verbosity on different environments, for example. But what if you want to pass a secret to the container? Kubernetes got you covered. There exists a resource simply called secret. Its task is to, keep secrets. There are several reasons why it's a different component than config map. Firstly, everything in a secret is base 64 encoded. And reminder, base 64 is not encryption. It's just how secrets are different from config maps here. Base 64 will mean it's just not human readable. So that's some sort of security, but it's still plain text level security. That's not how you protect your passwords, and it's literally one CLI call from being human readable. Anyway, so the base 64 encryption is here in the secrets only to facilitate the binary data that secrets can possibly have. An example of such a data is certificate. And this was how secrets were made originally. And right now, config maps can also facilitate binary data. So I'm just emphasizing this because there's a common misconception that why is it base 64? It's just for the binary data. Secondly, and more importantly, since secrets are a different resource, we can manage access to them. And we can manage access to them differently than config maps. For example, developers in a team probably don't need to access the secrets. They need to know that a secret exists and contains a set of data that can be referred to inside a container, but do not need to know do not need to have the access. We can just provide them. Another interesting security issue is how to inject secrets. You cannot simply inject them into runtime environment. Anyone can steal them by entering container by running env command and reading the output. And actually, let's see how stealing credentials in such a simple way would look like. So here's my console again. Uh, I'm creating a secret, and the secret will be called my password. The from literal flag creates an entry. I will create a password key entry that, well, stores password to my production database. Kubernetes tells me that it worked. Let's see if it really worked. Yeah, it worked. Notice there is one more secret present. It is created by Kubernetes, so it's irrelevant at this point. We can write the contents of the secret in the standard output. So in the data section, we can see password key and the value of it, basis for encoded. You can also see some metadata that was added by Kubernetes. And now I have a YAML description that I showed you kind of before. And the YAML description is a pod that injects the secret's contents to its environment. Yeah, I'll just run the kubectl apply to get it created. But it's a simple YAML template. It creates one container called nginx secret from nginx image. The only interesting part is this one. It, it we inject the password to the environment using the such syntax. So let's check what the password is by checking the environment of the container. I'm just executing env and grabbing for my password, and there it is. It's a very naive example, right? But it's really amazing how often people use default passwords to the services or store them somewhere in plain text. So let's clean up and go back to the presentation. To sum up, injecting secrets is not the best idea. Notice that I have very elevated permissions during the demo. So I'm using local minikube. I'm probably authorized as a cluster admin. But even if you take the permissions away and only grant me read type permissions, I could still steal the credentials. For example, I could craft a malicious container that logs its environment to standard output on startup and put it in the pod and use CA server to run it and just read the output. A better way of protecting secrets is mounting them as volume. You can mount key value pairs on file system in a specific directory, and they will actually mount file name with the key and value as content. It's an improvement for sure, but still it's not perfectly secure, but a bit better. Going on a bit of a tangent here, but Kubernetes is a relatively new technology, at least compared to, for example, Linux. And to make matters worse, it's a rather leaky abstraction, and the attack plane on Kubernetes is still quite huge. So access to Kube API should be well guarded. Luckily, several months ago, a bug bounty program was announced, and it accelerated even more the tempo of new bugs and vulnerabilities being found. Yeah, back to the presentation. Since deployment of the deployment of the application usually means deploying a config map. Uh, sorry, just got some technicalities here. Since deployment of application, it's not only it also means deployment to deploying config map and secrets. People started looking for tools to help them deploy, and one of the such tools is Helm. It's an interesting library. I'm having a lot of fun working with it lately. They have very active community, and it's yeah, it's a really cool tool. In the project that I work at, we use Helm to deploy our applications together with the corresponding config maps. Since we have multiple applications using the same configuration, such as database URLs or login configs, we're also using inheritance of configuration. This allows us to limit the duplication in our config files. So, for example, we keep the common environment values in one file, which is the most general one. Then we have some other files that are specific for an application, and we merge these two during deployment. Now, when deploying an application, sooner or later, you come across concerns such as logging, monitoring, tracing, etc. As I already mentioned, separation of concerns is one of the basic issues when designing architecture. And as we saw in the example of the git sync container, you want to decouple your main application logic and additional responsibilities. It's time we looked into what kind of containers we can have in a pod. Incidentally, there's a bit of confusion about the word pod. It originally came from the whale-themed vocabulary of Docker, and pod is a collective noun for a group of whales. The same way we have a flock of sheep, for example. So a bit of trivia here. The first special type of a container we have is an init container. As the name suggests, it runs before everything else does. It's something similar to a setup method in unit testing, maybe. That's how I compare it. So before we start performing the main part of the logic, we need some setup and delegate it to a separate entity. Init container is instantiated, it does its job and dies. Afterwards, the other container or containers are run. So several use cases for an init container that I taken from the Kubernetes docs are readiness probe waiting for another service to be created, registering a pod with a remote server, or parsing configuration templates. Uh, so parsing configuration files using information available after startup. So such an information could be pod IP, which is assigned during scheduling and is not known prior to deployment. Init containers are considered slow, so it's best to avoid them if possible. However, they do have their use cases, as I mentioned. Another type of containers are sidecar containers. How do they work? These are the auxiliary containers that do the work which is peripheral to the main container. Uh, let's come back to our example from the previous chapter. The container that hosts the application is the main or app container. The Git synchronizing container is the sidecar in this example. There are in fact three main design patterns behind the sidecar idea. I took this nice graphic from Matthew Palmer's website, and the two remaining ones will be also from his website. Yeah, so the first is as you can see, the general sidecar. You have a main application and communicate with another via file system. An example given here is log aggregation, so it's an interesting use case. It's also better to have the app container not be aware of the sidecar container. Excuse me. Another design pattern is the adapter. It kind of works like the adapter pattern from the Gang of Four book, but not really. We have an application container doing its thing and logging some output that we want to monitor. But the logs from the container are not something our monitoring tool expects. It expects a completely different format that it can digest. Our goal is to create a way for the monitoring tool to access the logs from the application without changing the application itself. Here comes the adapter. It will read the logs somehow from the application and expose it on a standardized API. It is essentially useful when we have different languages. Arguably, the most popular monitoring tool in the Kubernetes ecosystem is Prometheus. It's an open source project. It's graduated from CNCF, similarly to Kubernetes. You could safely bet on it being your monitoring tool. However, no architect will want to couple his application to a specific monitoring tool, right? In this sense, adapter can be treated as a dependency inversion tool. So the application might use an adapter that exposes a well-known interface to the application and also exposes API for monitoring tool to interact with the application indirectly. On the diagram here, we can see an example of such a setup. Applications, there are three applications, three pods. You have an application in Go, in Python, and in Java, and they are interacting with adapters. So on top of that, we can see external Prometheus log aggregation tool. And as a side note is that you can actually run Prometheus as a sidecar as well. So there are different approaches. The third example is the ambassador pattern. In this case, the application container needs a database connection. It can be also any other external service. It doesn't have to be database. It can be Kafka, whatever, some sort of object storage. Yeah. Instead of connecting directly, the application is connecting to the ambassador and uses it as a proxy. Now, why would we need such a proxy? Again, the answer is separation of concerns. Each container should do its task and do it well. In this approach, we will delegate the concern of connecting to the correct database to the ambassador. The application container will simply talk to ambassador and count on him communicating with the correct database. So the sidecar might modify how the application works without us changing anything in the application. And to wrap up, so far the sidecar containers were something informal. But starting with version 1.19, Kubernetes will actually make sidecar containers canon. So you will be able to actually mark a container as a sidecar in the definition, and not only call it sidecar. This will also have consequences in the lifecycle of a pod. So we know quite a lot how to design the pods, but there are still several loose ends. One of them is, how do we know if the containers inside our pod are running? And here's a simple, let's say, clever answer. Let's just ask them. Pods can expose so-called health checks or health probes for us. You can see an example on the slide. We will talk about two kinds of probes. The first one is a readiness probe. Kubernetes starts probing after the pod is scheduled, and scheduled means assigned to a node. The probe answers the question, did the pod start successfully? After the readiness check passes, the liveness probe is being run. It is run in some specific interval and ensures that pod is healthy. There are several types of the pods. This one could be running HTTP GET. It curls endpoints and checks what HTTP code it got. If it's between 200 and 400 with 200 included, it passes, otherwise it fails. You can also write custom probes in the form of a bash script. So what happens if the liveness check fails? Depending on the setting, the pod will eventually be restarted. And there's failure threshold, means how many times the liveness probe may fail. But it's usually low because even one failed live check means that the pod is not working correctly. And one story that I have, and it's a bit of anecdotal, is how bad implementation of a liveness probe can crush your entire system. There's a discussion what should be actually checked. There's always discussion what should be actually checked when the probe is run. And one thing you can have when you work with Java applications is Spring Actuator endpoint. you can easily configure the actuator to check all integrations before returning the result. So if you connect to database, Spring will go and ping the database to check if the integration is correct. It sounds good and surely has its uses. However, what if you get a hiccup on the database? Connectivity drops for several seconds, or database gets stuck for several seconds, or whatever. Such magical things, all the magical things that shouldn't happen, but they do happen surprisingly often. So what you get is a failing liveness check in your backend. And it's a liveness check that fails in your backend pod that connects to the database. And if this happens, Kubernetes might go and reset your entire backend. And it will, in turn, perhaps take down your entire frontend, basically tearing down your entire application and restarting it. I saw it happen in a controlled low environment, and trust me, you wouldn't like to have this in production. To finish off, I'd like to showcase the typical errors we can get in Kubernetes. The labels on the left-hand side refer to the status of the pod. So far, we only saw the running state and maybe container creating state as well for a moment. But yeah, first of all, scheduling. If a pod is stuck on scheduling, it means that Kubernetes tries to schedule the pod, but cannot find enough resources in the cluster. Solution, buy more memory or optimize the applications, but that would work as well, but it's probably harder to do. Next up, create container config error. That's a mouthful. And it means that you have something wrong in the YAML description of the pod. Now, as I mentioned, the declarative paradigm insists on using YAML templates of the resources. And about YAML, YAML is human readable, and as opposed to some XML files and other alternatives. Yeah, maybe depends on the file, but YAML has very good support for comments, and Google uses it a lot. And that's all the good news. There are also a lot of bad news about YAML. So YAML uses whitespace as formatting. Therefore, YAML files stop being fun after they're longer than, 10 lines. And if your YAML template is not working, you probably messed something up with whitespace, one space too much or too little. And it's fine when you're writing it by hand and you're using YAML parser, that's fine. But when you start using some sort of templating tools that create the files, like Helm, it can start being really annoying. But yeah, enough ranting. Image pool backoff. No such image or lack of connectivity to registry. And the worst of all, the crash loop backoff. The container cannot be started, fails during startup. To understand how the backoff ones work, we need to remember that Kubernetes uses self-healing loops. So suppose it tries to pull the image or start a pod and it fails. But once it failed, the desired state differs from the observed state. So it tries again and again and again. And the thing about the backoffs is at some point, Kubernetes says, all right, you know what? I'll back off for a moment and wait until somebody fixes it. It spares the resources that can be used in a better way than repeatedly trying to start up a faulty pod. However, unless someone actually does something about it, Kubernetes will still try to start the pod every once in a while. And importantly, it will display the number of tries. So how many times it tried to start up the pod. And several days ago, I saw a pod that had around 2,600 tries of being started because it was some old forgotten pod that was not working. So yeah, Kubernetes is not the most clever piece of software. All right, so that's enough about the pods. Now let's get to the juicy part. So rolling out applications. I already talked about the replica set. It's very useful because it has this declarative nature and self-healing loop. It's also responsible for maintaining the desired number of replicas. It is, however, not quite enough to perform deployment of an application. Imagine a scenario where we have a version of application deployed using a replica set, and we want to roll out a new version. So we create a new replica set. Two problems occur. First of all, we will have downtime. We cannot transition from one replica set to another. Second of all, what if the new version is broken or our application is not working as expected and we will want to roll back in such a scenario? We do not have any convenient way of doing this with replica set. However, there are deployments. Deployments are basically one step up from replica set. They not only control what replica set is deployed, but also version of the replica sets. This gives us some useful functionalities. For example, we can track the versions and annotate them. Another cool thing is that we can roll back anytime. If something is not working like we want, we just roll back and the application goes back to the state described in the previous state. But possibly the best functionality, and this is the one that has gathered the most hype at the beginning of Kubernetes, is the rolling update. And here's how it works. We have a replica set running three replicas of an application with version 1. We tell Kubernetes to roll out a new version 2. Here's how the rolling update happens. First, one of the pods in version 1 will be killed, and a completely new replica set will appear with a pod of version 2. Kubernetes will wait until the version 2 pod is ready. So we'll wait for the readiness probe to pass. And once it's ready, the rolling update continues. After several steps, we are left with a new version of application. There are two factors that we can control here, the unavailability and surge. The unavailability tells us how many pods may be replaced in each step. So here we had around 33% unavailability, so we went one by one. It would be nice to have very low unavailability, but the lowest possibility is going one by one. We can also increase it to, for example, replace two pods at a time if you want a quicker rollout. There's also the surge, and the surge tells us how many more pods we can have. Here we also have 33% surge because, we create one additional pod. Ideally, it would be nice to go as high as possible, but remember that we're temporarily using extra resources, so there's a bit of a balance how quickly we perform the rollout. Another note, since Kubernetes will always wait for the readiness check of the new pod, you won't be able to replace a working version 1 with a non-working version 2. It will never move past the first step, so it will never go past here. If such a scenario happens, you will be easily able to roll out and stay with version 1. And yeah, I initially planned to show this in the form of live demo, but it's a bit difficult to show it unless you have a nice graphical user interface for Kubernetes. Networking. So networking in Kubernetes is problematic. Every time we create a pod, it gets assigned to an IP assigned. This IP is ephemeral and lives as long as the pod lives. So let's look at the example. We have a replica set with one pod, and the pod has some IP address. We also have another pod deployed with a container that is dependent on the top one. The container uses a fixed IP, so it's put in here, and they can communicate at this point. Everything works fine. However, at some point, the first pod has an out-of-memory error. Its liveness probe fails and it is killed. The container on the bottom loses the connection, which is expected. The replica set notices that desired number of pods is different than the observed state and creates a new pod. Upon creation, the pod gets a new IP address assigned. As a result, even though the first pod is running, the second pod still cannot access it. Excuse me. The solution here is using a service. The service is a Kubernetes resource that plays many roles. The first role is providing a non-ephemeral endpoint. When a service called main app is created, it gets its own IP address and a DNS entry is created that resolves the name of the service to its IP. So if we point the container to the name of the service, we'll always get it resolved and communicate with the service. The second thing it does is proxying. The traffic going to the proxy will be, well, proxied to the pods based on their label selectors. So if we have a service that selects pods that have a label main app, we will just create a pod with that label and have traffic directed to it. So let's look at the example from the previous slide. Instead of using an IP, we can just pass the name of the service and expect the service to always direct the traffic to the correct pod based on its label instead of its IP. All right. The last important role that the service plays is load balancing. Service will distribute the traffic throughout all eligible pods, and also in the example, only two pods are working correctly. So only two of them are healthy. The third pod on the left-hand side is marked as unhealthy. Maybe it just got created and didn't pass readiness probe yet. That may be one of the reasons here. In such a scenario, traffic is not routed to it. There's also a resource called endpoint that gets created, but that's not important to discuss at this point. We'll only focus on the services. All right, let's put it all together. Let's see what an application working on Kubernetes is made of, based on all we've had shown here. First, the deployment resource. It contains a replica set and a version of the currently deployed revision. The replica set contains several pods, let's say 4 of them. It will constantly monitor the number of existing pods, and if any of them dies, it will create a new one. Let's look inside the pods. Let's go even deeper. We find 2 containers there and a shared file system. We may suspect that one of them will be our main container and the other will be some sort of a sidecar. We inject some environment variables to the containers, mount some secrets, for example, credentials. We also expose one of the containers, for example, via service resource and allow traffic in. And we're basically done. That's how basic server application can be hosted in Kubernetes. There's also a bit of other things such as security related stuff, etc. But yeah, this is the, let's say, general picture. So, last chapter of this text talk, I promised to go over some internal tooling of Kubernetes and show how this technology itself is built. So let's have a look behind the scenes. I'll only go through several of the components, those that are, in my opinion, the most important ones. There's a lot of happening in the networking layer, as I mentioned, and a lot of happening on the security layer. But networking and security in Kubernetes is enough for an entire another tech talk, and there are many great talks from, for example, KubeCon about it. So I'll only focus on the 4 main pieces that focus on the general picture. The first piece of the puzzle is the Kube API server. This is the API layer I've shown at the beginning, and it's an application that runs on the master node and exposes a REST API. Suppose we have some sort of definitions here. Yeah, definitions of deployment, config map, service, maybe some more, and they're all stored as YAML files. So we can use, for example, kubectl client, and we are effectively running REST calls to it when we create the resources. So when we post something to the API, the Kube API server, it will take the definition of the, for example, pod and store it in etcd, etcd being a distributed key value store. It's basically all the API server does here. So there's the security layer, of course, and some other features, but logically it's just an API that saves and fetches things from etcd. And yeah, it's an API gateway. Next up, scheduler. There's a well-known analogy to the Kube scheduler. Scheduler is like a waiter in the restaurant. So it sees some people that are coming through the door and leaving, knows how many tables it has and how many of them are empty, how many occupied, and its main job is directing people to the tables and seats. So what the scheduler does in the context of Kubernetes is it watches the API server, and whenever a new resource appears in the API, for example, 5 new pods to create, it looks at the resources of the cluster, looks at the nodes, and schedules the pods into the nodes. It makes sure that the resources needed by the pods are available at the node. And also there are multiple ways of influencing the decision of the scheduler. You can completely replace it as well, because pretty much everything in Kubernetes is replaceable. I've heard about schedulers being written as several lines of bash. So apparently it's not that hard to do if you want. However, the default scheduler is also doing kind of load balancing, let's say. So it tries to distribute equally. Next, the Kube controller manager. And in order to understand the controller manager, we need to briefly discuss controllers. So a controller is a process that handles routine tasks in the cluster. That's, say, the definition. We already kind of talked about one of the controllers, the replication controller. His job is maintaining the correct number of replicas in the replica set. So as you can see in here, it ensures the observed equals desired, and the replication controller terminates any pods which are above the limit, and if there are too few, it will start new pods. And basically the controller manager is something that's on top of them. It continuously let's say, pings the Kube API server. It's watching it, and whenever something new appears, for example, we request the number of pods in replica set to be changed, the controller manager will update the relevant replication controller and tell it to change the desired state. And then the replication controller does the heavy lifting. Kubelet, the last piece I want to discuss here. And Kubelet is an application running on all worker nodes. And depending on the setup, it will probably also run on master. It usually does. Pretty much everything that Kubelet does is running the containers. It has an embedded container runtime engine. It's usually Docker engine, but there are many options. And whenever it sees that a pod has been scheduled to the node that the kubelet is on, I marked it here, it creates the container. And that's the most important task of the kubelet. But let's say there's some more responsibilities of the kubelet because it's responsible for the node. It, first of all, registers the node with the API server. So It is an agent running on the node and changing the virtual machine into, or physical machine, into a part of cluster. Also, it is kubelet that performs the readiness and liveness checks. So far I'm just referred to them as being magically performed, but it's kubelet doing the work. And it also reports the state of the node to the rest of the system so that the master knows whether a node is healthy or not. All right, that concludes my presentation for today. And right now, let's get to the questions. Now, if you have any questions, write them in chat. I see there are already some questions. I'll try to answer them. Also, there is a slight delay on the stream, so my reactions will be a bit delayed. Okay, one question is that what about Nomad? That big criticism of Kubernetes is that it's an overkill. And yeah, Kubernetes is a huge system, and surely it has a very steep learning curve, and even say professionals, so people who work with Kubernetes, let's say on a daily basis, say that it's just a difficult technology and there are multiple moving parts there. I don't know much about the Nomad actually. I've heard about it, and um, yeah, I suppose there will be a lot happening in the Kubernetes environment ecosystem to make Kubernetes as simple as possible. So yeah, but yeah, it's definitely a complicated system, and if you just want to use it to orchestrate containers, then you can probably find a simpler solution. Right. There was a question that will there be recording available? So yes, this live stream will be posted here on the Netcompany website as a video, um, probably in the several weeks, maybe a week. I'm not sure what's the scheduling here, but yes, it will be, and it's something like between 1 or 2 weeks. That's how expected. Will the presentation be available? So the presentation if you meant the talk, then yes, it will be available. So yeah, another question I got is in what situations? So what are the advantages of using replica set instead of deployment? So practically, you will always want to use deployment and let's say rely on deployment to create replica sets for every version that you deploy in the context of the deployment. So I don't think I saw any, let's say, replica sets being explicitly defined, but so we just declare a deployment, and it handles doing the creating replica sets. Right. Next, about namespaces and have you been using text? Okay, okay. So there's a question about namespaces. So so the answer is you can use namespaces to create environments. Yes, and I think it's a decent idea. You can even use namespaces to create, let's say, sub-environments. So for example, when you have a layer of applications, so only the applications, let's say, so no, Spring Boot applications, you can put them in one namespace. And you can use another namespace, which is still the same environment, and put the, say, middleware layers. So on lower environments, you can host a test database as a container in a different environment, in a different namespace. Or you can just create one namespace per environment. So the thing is, at some point, you probably want several clusters and at least separate low environments from high environments, because they will definitely have different policies, the different governance there. And you can, in this case, use namespaces inside one Kubernetes cluster to create different environments. And this is fine because you do not create multiple clusters. So you do not go with one cluster, one cluster, one environment, but you just host several environments in one cluster. This is fine. Yeah. But yeah, again, as long as you remember that your highest environment or maybe two highest environments should be separate clusters. Mm, okay. Next question that I see here is about replica set. So does replica set contains definition of only one type of pods? I think it only has so I think the replica set only has one pod and we just give number of replicas of it. So the only, let's say, thing that we add to the pod will be number of its replicas. And I think it's the same with deployment. At least usually what I saw is if you want to deploy different type of pods, you just wrap each of the pods in its own deployment. At least that's the approach that I saw. Uh, Maybe you could deploy several pods. I'm not sure, to be honest. It's best to separate them so that one deployment has let's say one pod defined and it creates replica sets. All right, I do not see any more questions. So one last note maybe I'll just make is that possibly the coolest thing Kubernetes caused was building a wholesome ecosystem around it. And there's a lot of open source tooling related to it. And if you're looking for a place to start contributing to open source, I'm sure you can find something in Kubernetes ecosystem. And yeah, that's all we have time for today. So thank you very much for tuning in. If you enjoyed the talk, stay tuned. There will be more tech talks coming. And this talk, as I said, will be available probably sometime in next week or next 2 weeks. So yeah, thank you again.